Yeah, thank you very much for the invitation to speak in this nice event, in this nice place. I will be talking about Resurgent large genus asymptotics, and this is joint work with Ena, Giacchetto, Gregory, and Levansky. So our goal is to compute or to understand the behavior of intersection numbers. So you don't really need to know what intersection numbers is. You will see a working definition on the moduli space of curves at fixed n and large genus. So we're going to take two integers, g and n, and we only want to consider the stable cases. So these guys behave nicely enough. So we want to take 2g minus 2 plus n to be strictly positive. And now we consider the moduli space of Riemann surfaces of fixed genus G with n marked points. And we take its the linear Mumford compactification. So we take also nodal curves. We allow also nodal curves. And, ooh, this is complicated. And yeah, that's what the bar means. But you don't need to know much about this. And basically, we're going to compute large genus asymptotics, so we want to understand what happens with when the genus grows of these nice important numbers that appear in geometry. So I lost my talk. Good. So let me introduce things a little bit. Maybe I should keep a little bit track of time. So we care about certain intersection numbers. The good thing about this project is that we are able to attack many different problems with the same techniques. So I'm going to talk most of the talk about the most basic intersection numbers, also kind of the most important because it's the building blocks for many others. But the nice thing is that we will be able to apply this to other intersection numbers. So those are the so-called intersection numbers, or also psi-class intersection numbers. So this is just the notation for these intersection numbers. They depend on a tuple of these. And they are just integrals over mg and bar of certain cohomology classes. That are called the psi classes. These guys will be just rational numbers. Okay, maybe you need to know that they will be different from 0 only if we have that the sum of this has to be equal to the dimension of mg and bar. So if we have this condition. Okay. Okay, and then I don't want to say much about this. Maybe in the end I can explain more if we have time. But we will go directly to try to study the behavior when G is large. But of course I will mention one of the most classical results about these numbers. So geometers cared a lot about these numbers, but they were only able to compute them when G and N were very small using geometry. And then Witten arrived, he gave some interpretation of these numbers relating them to two-dimensional topological gravity. And then using that, he was able to match them with a solution of the KdV hierarchy. So this is something that made these numbers even more important and computable recursively, with a recursion that is a bit slow. So that's why we still care a lot about what happens when genus is large. If we can get something specific about that behavior, that's quite nice. Let me also mention that these numbers are also quite important in combinatorics of maps and volumes of metric ribbon graphs. So they are quite important numbers in many different fields. So theorem, that was Witten conjecture from the 90, and then it was solved just 1 year afterwards by Concevit, says that if you package those numbers into a generating series, I'm calling it the Witten-Concevit generating series or partition function. So just take exponential, you sum over all possible GNNs. You put an H bar that will keep track of the topology. So it's just to the power 2g minus 2 plus n over n factorial. And then you take sums over all possible tuples of these that are just the degrees of our psi classes. We plug our intersection numbers, and then we have our formal variables that keep track of these intersection numbers. So this guy will be the solution of the KdV hierarchy, so the Korteweg-de Vries integrable hierarchy, plus an initial condition that is called the string equation. Okay, so this is very, very nice because this allowed to compute these numbers recursively. So with geometry, people were able to compute the first cases. So for genus equal to 0 and equal to 3, and for also for 1, 1. And with that, you plug them into the hierarchy, and with the string equation, you are able to compute all of them recursively. Okay, so I also want to mention that this result is equivalent to what we call topological recursion. I will say very few words about that. But before going to that, let me here tell you, so I said that we care about behavior of intersection numbers, so not only this. This will be my main example because it's the simplest and we understand everything very well, and it's a bit more pedagogical to present just this. But we also care about other examples. So there is another example that is interesting and that is easy to present having said all this, because we just need to say, so now this is very bad because I think there are no colors that I can actually distinguish from white, but let's try. I'm not sure this is better. Okay, let's go with red, and hopefully it will be kind of clear. So if I add this theta there, what I have to do to this intersection number, so this is just a notation, right? So I can add here a cohomology class that is quite interesting, that forms a cohomological field theory. So basically it has nice properties. And it turns out that it was conjectured by Norbury in 2017 that if you put now here, instead of Witten-Concevit, you put VGW. This is Bresson, Gross, Witten. So it was already a solution of the KdV hierarchy that was studied in the 80s in the context of physics. But what was not known until recently, so this is what Norbury conjectured in 2017, is that there is also an interpretation in terms of enumerative geometry. So you need to plug these cohomology classes in there. And then this will still be a solution of the KdV hierarchy with, of course, a different initial condition. So plus different initial condition. Okay, and this conjecture was solved by Chidambaran, myself, and Giacchetto in 2022. So, okay, in this large genus project, that was also an interesting problem for us that gave us different features from the classical Witten-Concevit intersection numbers, but that fit our formalism very well. Okay, can you see? Yes. Good. Okay, so I was saying that the fact that this generating series satisfies the KDV hierarchy plus the string equation is equivalent to this topological recursion. Let me say a few words about this. We actually don't need topological recursion of the KDV hierarchy at all in this project, but topological recursion and the fact that we can relate it to many, many things helped a lot building the right strategy that is the most universal possible to be able to find this large genus asymptotics. So I think it's worth mentioning it. So I abbreviated TR. This was invented by Chekhov and Arnaud-Antin around 2004, 2007. And it's a procedure, so I will say just a very few words. I guess most people maybe heard of it, but just in case. So it takes a Riemann surface. So this is the input data that is called spectral curve. And it consists of a Riemann surface, then two meromorphic functions on it. And with these two guys, we can build a one form, which is usually y dx. So it's a one form on the Riemann surface. And then as initial data, we also have omega 0, 2, which is a B differential on sigma. And then topological recursion tells you, so I'm not going to say anything about how the formula works, unfortunately, but it tells you that there is a procedure to compute omega gns for any gnn. And these omega gns will be n differentials living on n copies of the curve. So this is the idea. And why is this so nice? It's very nice because with this simple data, it turns out that if you change this simple data, you can solve many, many different problems with the same universal procedure. So in the sense that these guys will be computing interesting numbers in geometry, in physics, in combinatorics. So for this specific case, I was saying that solving the KDV hierarchy plus string equation is equivalent to topological recursion. So I have to say on which spectral curve. So it's on the Airy spectral curve. So I will tell you what it is. And for the other case, the case with the theta class, it's on the so-called Bessel spectral curve. Okay, yeah, and the spectral curve consists of, now the Riemann surface is like very simple. It's just CP1. X will be equal to z to the square. Will be equal to z. And omega 0, 2 will just have this term that is very characteristic of the omega 0, 2 with a pole along the diagonal. And then what happens for the Bessel? It doesn't change much. The x is the same. The Riemann surface is the same. And then the omega 0, 2 is also the same. Just the y changes. So the y will be 1 over z. That's the only difference. So you run this universal procedure on these two spectral curves. You will find omega gns whose coefficients will be those intersection numbers. Okay. Yes, it also has a matrix model interpretation. And actually, this was kind of the definition of this BGW partition function. Like the definition kind of comes from the matrix model. It's just a matrix model with a log term. And they are both equivalent to Virasoro constraints as well, just different Virasoro constraints. So it's a nice parallel story that was solved just recently. Okay, so but yeah, I don't want to get too distracted with the background. I could talk for hours just about these stories, but let's try to see some resurgence here. So the point is that, okay, in principle, we can solve theoretically these problems. We can compute all intersection numbers with these recursions. But these recursions are slow. And also, it's expected in many cases that the behavior of certain problems when the genus is large has nice features. Nice features that, that are difficult to capture with these slow recursions. So that's why we care about directly finding the asymptotics of the problem. So it's kind of an important problem. So theorem that was actually solved by Agarwal first, and this was in 2021. Then it was also solved in a different way by Guo Yang in 22. And then I will also present our solution. This is mainly what I will present. But first I want to comment about why we cared about giving this other solution, right? So first I present the result. So uniformly in D1, Dn, and when the genus grows, so it's very large, the behavior of these intersection numbers is understood. So first I want to introduce a little normalization that will be useful during the talk because it will save us some time writing these factors over there. So I want to give a new name to these guys with these products. So I'm just gonna call them the same but with this double triangular bracket. So sorry, here there's a genus, here there's a genus as well. And so the result is that this has the following behavior when G is large. Okay, so this was conjectured already by several people, Delacroix, Zorit, Goujard, I think that's it, maybe Sograf as well. And this was solved by Agarwal. First, let me comment on Agarwal's proof. It's really impressive, Agarwal's proof. The only problem, if you want, I mean, it's still a very nice proof. The problem is that it's very ad hoc. It's very specific for this problem. So it doesn't work, for example, for the theta intersection numbers or for other intersection numbers, or for even other combinatorial problems. Same with Guo Yang. One nice thing that Guo Yang did is that they also conjectured the subleading corrections, which is very nice because of several things. One is that if you add just one subleading correction, you are already very close to so the error is very small. So it improves quite a lot, these leading asymptotics. And it's also very nice because they have a very nice structure, the subleading corrections. They conjectured kind of certain properties that should determine the subleading corrections. So in principle, all of them, but a bit theoretically, like there's kind of an algorithm to compute them. And you see with this algorithm that they have nice structure. Okay, so several questions arise. One question is there a universal method that would work for almost any problem? I mean, almost any problem maybe is a bit saying too much, but we have many problems that fall in the scope of topological recursion. So our question was, could we develop a method using some generic things that are available to us and that seem to be related to topological recursion that would work for any problem satisfying topological recursion? And what we did is actually develop a method that works for many problems that satisfy topological recursion, but not the most complicated problems that satisfy topological recursion. So we think that in the end, it should work for all the problems satisfying topological recursion. For the moment, we have some hypotheses. So, but because we really wanted, this, by the way, was born out of another project in which we were computing instanton corrections for JT gravity, so Weil-Peterson volumes. And in that case, it was really, this was questions that the physicists gave us, and we were able to compute them, but we were not able to prove things. We needed like very strong hypothesis of resurgence. So yeah, I don't know, my inner mathematician was like, can we actually prove this for certain class of problems? And this is how this project was built. But you will hear about the other project next week. The people that are here, Paolo Gregory will talk about that. So, okay, we developed this universal method, or kind of somewhat universal method that we aspire that it will be even more universal. And it's based on resurgence and integrability. And this is what I will present today. Then another question that arises from Agarwal's proof and, well, from this result is, can we give certain geometric interpretation to this result over here? And this is also provided by our method. And the next question is, can we actually compute the subleading corrections? And can we actually prove the subleading corrections that Guo-Yang conjectured? And this we can also do with our method. So we can solve these three things. So let me first present them. Like this, you already see the final result, and hopefully you're motivated enough to see how to do it. So yeah, maybe the geometric interpretation, I can give it here. So we will have a constant here that I will call S. In this case, of course, S is just equal to 1. But this constant will have a meaning. It will be the Stokes constant of a certain differential equation. So in our case, what happens is that so a bit of geometric interpretation. We have the area spectral curve. So just, you can write it like this. And you can do what we call the quantization procedure. So you turn it into a differential operator. In general, this is a quite complicated procedure that is quite technical to prove, so don't think that it's just straightforward. In this case, nowadays, we know so many ways of proving it that, okay, maybe you can think that it's straightforward. The nice thing about this quantization procedure is that the classical spectral curve helps you build both the operator, the quantum curve that is called, and the solution. So you can build both out of it. And now we know how to solve it in many cases, and our method depends quite a lot on this quantization. So this is one thing. So this will be this constant appearing there. That will be the Stokes constant that comes out of that differential equation. And then also these 2/3 it will come out of, it will be, so we can call it A in general, and then it will just change for the other cases that we are able to solve. And it comes out of the exponential growth of the solutions. So it will be, they will be of this shape. Exponential plus minus A over h bar x to the 3/2. So the 2/3 is exactly the exponential growth that appears there. And this gives the interpretation for that. And then we are also able to produce this. So let me show you which shape that will have. So it will also have to do with this A. Then you see some coefficients appearing, and this is the guys that will have a method that allows you to compute them. And that was conjectured in Guo-Yang. And here you see this. So I need to introduce that notation. So what I mean is, when I write this, I just mean x times x minus 1, x minus k plus 1. Okay, this is exactly what that notation means. So this is the shape of the subleading corrections. And we will still have order minus k minus 1. Order of j to the minus k minus 1. Okay, and another little comment that I can make is that these alphas, they are computable. They are actually computable using the subleading corrections of the solutions of the quantum curve. So, and we have full control on that, so we can compute it. So you can already start guessing which are the hypotheses that we need to put for this to be solved by this result. So we need to be able to control all the subleading corrections of that, and that is not always possible. And we don't even always have these quantum curves. Like, for example, for Weil-Peterson volumes, we don't really know what the integrability part will be. So this will be a polynomial in n and a polynomial in multiplicities of the di's. So it will depend on how many di's you have equal to 0, equal to 1. So it still has that dependence on the di's. Okay, so this is enough for the introduction. Are there questions there? Yep. Exactly. That's exactly the coefficient of the instanton action. For us, what we call the instanton action is this whole thing. And that's exactly the right interpretation. And you will see it appearing there exactly from this kind of well-known result in Resurgent, but that was very hard for us to find a proper mathematical proof for it. But it will have to do exactly with this result that relates large order behavior of a perturbative series with the first instanton corrections to the series. So this will be our next part. Are there other questions about the introduction? I think so, because you can get the, I mean, it depends on how much you know about your solutions of the KDB hierarchy, but in principle, you can get the quantum curve out of the hierarchy. And that gives you already several things that we need. Okay, there's another thing that you will need to prove, but maybe it can be done just with the hypothesis of being a solution of the KDB hierarchy. So we will be using basically this resurgence principle that I talked about and that I will present now, and then the determinantal formulas. The determinantal formulas are not known for any solution of the KDB hierarchy, but I think you can prove them, because I think you can even prove them for solutions of the KP hierarchy. Of course, you need something that specifies which solution, so I think you can prove it. Yeah. You just need enough conditions for the solution to be unique and for the solution to satisfy a determinantal formula. So you need to be able to prove the determinantal formula. My guess is that you can prove it for any solution, the determinantal formula, but that I'm not completely sure. It's a bit wild guess. We know more or less that sufficiently simple problems that satisfy topological recursion satisfy the determinantal formulas. It's just maybe not super well and cleanly written mathematically anywhere, so we didn't want to use it widely. We just used it in the cases in which it's very well written in the literature. In other cases, one needs to do a bit more work and prove it, but I still think it's true. No, not really. So if you think of targets in that sense, for example, of the cohomological field theory, that is really just a point. And that's it. So CP1, the CP1 that appears here, it's just the spectral curve on which things will live, but it doesn't have to do with the target. No, so, but it will be very interesting. I mean, the point is that we wanted to build this universal method. We applied it to the class of problems that where everything was crystal clear and we could prove everything. And we had enough interesting features because we basically solved several problems with different nice features. Now the next steps will be to apply this to many other cases and even to make it as general as possible. And in that case, in principle, it should be true as well. But there could be technical problems like finding the quantum curve or proving the determinantal formulas. That is still to be done. Okay, one could make conjectures. This would be very easy. We could have done a paper with conjecture. Everything works and okay, but we would have need also some effort to say, okay, are these conjectures really true? Like, okay, and we didn't want to do that. We wanted to do really a paper in which we could prove everything. Yeah, that's another possibility. That's what we did in the other paper, by the way. So we are fine with both. Just in this paper, we focused on like, let's do what we can for sure do mathematically. So okay, let me continue with the first part of the talk, resurgence, large order behavior. So maybe what I will present will be very basic for many of people in the audience, but at least you can see what we were able to prove mathematically clearly, and yeah, could be useful. Because of course, we spent a lot of time at the beginning of this project figuring out the other part, thinking this was true, thinking it was even proved somewhere, but in the end we couldn't prove it. We couldn't find it anywhere. So we proved it in the cases that we needed. So we take a series that is divergent, but we want its Borel transform to be convergent in a disk around the origin. So this is the notation for the Borel transform as usual. So basically, phi hat is analytic at the origin. We suppose its analytic continuation has only one logarithmic singularity. I mean, in the end, we can prove it, of course, also with more singularities, but let me state it in the simplest possible case. In the paper, it's proved in more generality. So it has a single logarithmic singularity. At A, so kind of the coefficient of the instant on action. So, and of course, we don't want that to be 0. And what do we mean exactly? What do we need to be able to control? So this is visible, yes. So this guy will have the shape of our Stokes constant. That of course, if you just see this result, you wonder why do you put this constant there? You can just put it inside the guy that will appear here. But we put it because it makes sense when you try to do this geometric interpretation. They appear separately, the Stokes constants and the minor there. So here we have what we call the minor. This is the Stokes constant. And here we will have our log singularity. And then the rest will be holomorphic at A. Okay, and then we also need to know, since I mean this should be the log singularity of this guy, and this should be holomorphic at A, so psi hat should be holomorphic at 0, and then it can be expanded. And yeah, we will use these coefficients. They will appear in the formula for the large order asymptotics. And then we obtain that AM is just of this shape when M is big. So okay, probably you're very familiar with these expressions. Maybe you even use them sometimes. And you can find some nice explanations for these expressions using, for example, alien calculus and this stuff. In our paper, we just proved it in the most elementary possible way. And the idea is quite simple, so I can present it so it's clear for everyone, even people that maybe didn't see this. The idea is quite simple, then the details take quite a lot of work, I have to say. So the idea is that, that we can compute the coefficients AM of the Borel transform, since it's holomorphic at the origin. We can compute them using Cauchy formula. So you just need to take a contour of 0 that is small enough, and nothing goes wrong. Okay, so just take a contour of 0. So you have your singularity A somewhere there. And you just take a contour that is just smaller than the singularity. So no problem. But then you can wonder what happens if you start enlarging this contour. So of course, at some point it will start interacting with the singularity. Okay, and then at some point, and this of course I'm already putting under the carpet many, many technicalities, but at some point you will only care about this Henkel contour around the singularity that we can call H. So in the end, you will be able to write this as just an integral on this Henkel contour. Then the next thing you do is to plug this formula in here. You know that the log, of course, has a singularity there, and you know how that behaves, so you're able to compute, and in the end, massaging a little bit, you will get such an expression. And you will have that these expansions of psi hat will play a role, so you see the coefficients appearing there. Okay, so this is the idea for this. The main example is again the Airy function. So if you take formal WKB solutions, this will still not help us solve the enumerative problem that we want, but it's the first example that you can apply this theory to. So you take the formal WKB solutions of the Airy ODE. The Airy ODE is what I wrote before, so it's just this guy. And then you will have what we call usually the Airy function that we denote as psi minus. So it will behave as this exponential with the minus action there. And you see that the action actually depends on x in these cases. That's because of, like, we are treating these instantons that are of type FZZT, I think they are called. And a of x will just be 4/3 x to the 3/2. And another thing that I want to mention is that these CKs, we can compute them explicitly. And then we have the Berry function. That we denote as psi minus. And we know that it's just the Airy function, but on minus h bar. Okay, so we know everything about this. And one nice thing is that we know the singularities of these guys, and we know that for the Airy function, we will have the Berry function appearing as the minor and the other way around. So let me write this down. So this will be the Borel of the Airy. And for that, we will have that the Berry function will resurge. So this little instance of resurgence. So we say that the Berry resurges at the singularity of the Airy. And so for Airy, we can know everything. We can know that where is the singularity located, what is the Stokes constant, and what is the minor. And we know that the singularity will be located at a of x, that the Stokes constant will be 1, and that the minor will be just the Berry function. Okay, so these pretty basic things, but okay, it's a summary about this resurgence large order behavior that we will need to compute our large genus asymptotics. So maybe I will not make a pause for questions. I will just continue because otherwise I don't have so much time. And then we can have questions in the end. So the second part that I want to present is the determinantal formulas. This is the second key ingredient that we need. So we take our endpoint generating series. So another point is that, okay, we can apply the resurgence principle to this Airy, for example, and that seems to be related to the problem of intersection numbers, but it's not what we need to solve the large genus asymptotics of the intersection numbers. What we will need is the endpoint functions. The endpoint functions are the guys that will be computed by topological recursion. So this will also carry an h bar that will keep track of the topologies. So maybe I will just write it like this. So you can just see it as a generating function for intersection numbers. So it's a generating function for the omega GNs where we vary the G's. And the omega GNs are really generating functions of the intersection numbers that we care about. So I'm just basically most of the time doing just the case of Airy, but putting the generic name so you can see what you need to change to solve other problems that fit in the same framework. So you will see our intersection numbers that we care about appearing there. And here you will have these denominators that keep track of the DNs. So basically, H bar keeps track of the topology, and the xn's, xi's keep track of the d's. This is how you should think of this generating series. And now the determinantal formulas tell you that if you take the airy kernel, so to define the airy kernel, we will need epsilon that can be plus or minus. The plus or minus will be referring precisely to this plus or minus here. So we define the airy kernel as k epsilon minus epsilon. So it will be a kind of 2-point function. It depends on x and y, and also h bar. And here, okay, and I forgot to introduce one notation. So basically, I want to call all this guy the guy without the exponential. I want to call it psi minus tilde. Okay? So maybe it's a bit hard to now add this, but I will do it here. That will be psi minus tilde. So okay, with that notation in mind, what we want here, you will kind of see why this is enough to take these guys. So you build this kernel like this. I remind you that I'm building the kernel in which you put as appendices epsilon and minus epsilon. This will have the shape of typical integrability kernels. So it will be of this type. And this allows us to compute in a quite interesting way the endpoint functions. It's interesting, and it's also very useful. So for large genus asymptotics, we were thinking for a long time, what is the best tool that will allow us to access the large genus in the better way? And in the end, the determinantal formulas seem to be winning. So basically here we want to take sum over permutations that are of a certain type. Now I'm taking sum over permutations that are just one cycle permutations, and the cycle has to be of length n. This is what this notation means. And then we will see products with n factors of these kernels with epsilon and minus epsilon. This is very important. And here we will have xi and x sigma I. Okay, and now important thing that I said but I didn't write. This is just one cycle of length n permutations. So I just want to take sum over all those permutations of that type. Sorry, length n. Okay, so maybe I want to say some comments about this, because I think this audience can understand this quite well. So it's quite important that here you have products of two guys. And you will always have, since you're writing here epsilon and minus epsilon, you will always have here epsilon and minus epsilon. Okay, you have derivative, but derivative has the same type of exponential behavior as the non-derivative. And since you always have these guys, even if you don't put, sorry, this is nonsense, I just wanted to put tilde. Even if you don't put the tildes, you put the original functions, because in principle, this guy works at the level of non-perturbative things. So you can put the things with the exponentials, and it should behave nicely. When you plug these things in here, even without the tildes, all the exponentials will go away, because you will always have exponential with a minus and exponential with a plus of the same thing. So that tells you that this part that is computed here is the perturbative part of this guy. And this is actually, this can be seen just an asymptotic expansion of this guy that is actually a non-perturbative object. And what we will do is we will see that the guy that will appear attached to the singularities of this guy will be the one instant on corrections of that guy. and we are able to guess what they are easily, and then we are able to prove that they are actually what appears there. And then we are also able to massage them a lot and compute them very explicitly in those cases, and this allows us to compute the large genus asymptotics. So this is the idea of the end, but I can also do it. Maybe I'll do it there. Now we can pass to more questions. These determinantal formulas are also very useful, even not in the context of large genus asymptotics or resurgence. So they are very deeply related to integrability. So singularity structure, we need to control the singularity structure of our endpoint functions. I will here, and it will allow us to conclude. So we understand perfectly, as I said before, the singularity structure of the airy and berry, or the whatever solutions you have for the case that you are solving. And this implies for you, because of this formula, you see that those are the building blocks for the endpoint functions, and probably you can guess a bit how this will work. This took us some work, but it's not too hard. So this gives you the singularity structure of the Borel transform of the endpoint functions. And you will see that they have 2n logarithmic singularities. At least these will be the singularities in the principal sheet, and those will be the singularities contributing to the large genus asymptotics. So it will have 2n logarithmic singularities at u equal to epsilon a of xi. So u, remember, is my variable for the Borel transforms. And I runs from 1 to n. That's why that gives you 2n singularities, because epsilon runs from plus and minus. The Stokes constants you are able to compute as well. In this case, in the other cases that we do, they are a bit more complicated, but you can also compute them. And now I can give you exactly the shape of how the singularity structure of this will look like. So you have your Stokes constant appearing there. And then you will have this kind of first instanton function appearing here. Attached to the logarithmic singularity. So we are always working with simple resurgent functions. Then things are simpler. But this was a bit of a choice. Depends. You can move things a little bit and turn them into other types of singularities, and that is fine as well. And this is the Borel transform of this guy. And I can give you the shape of this guy, and that will connect to that. You will probably understand why this computes the first instanton corrections. So here you will have, again, sum over permutations with just one cycle of length n. And you will have kernel appearing with minus epsilon minus epsilon. That gives you precisely that when you put together the two guys with exponential to the same sign, they will not cancel, and they will give the instanton corrections. And since we are only caring about first instanton corrections, the rest will still be like in the perturbative guy. So it will be k epsilon minus epsilon xj x sigma j. So you can imagine how that is the first instanton correction. And then corollary that really allows us to conclude. Maybe I stop here and we go to questions. This really gives you the large genus behavior of this generating series that eventually, after massaging and developing some tools to compute the first instanton corrections, we are able to transform into the large genus asymptotics of the numbers that we care about. Okay, so I don't have a lot of space, but I continue here. So we have that coefficient, and then we sum over I that goes from 1 to n, epsilon that is plus or minus. And here we will have all W0n. So kind of first guy appearing in the expansion of this, which is the first instanton function. And this will have a denominator that will be epsilon a x of I to the 2g minus 2 plus n. And then you have also some other guys appearing. So this is everything inside the sum. Sorry if it's a little bit messy. Then I can just say with words the last part. We can actually compute very nice formulas for these guys that are the nice formulas that in the end allow us to extract the asymptotics of the coefficients properly. So yeah, basically this is it. Thank you. Yep.
A couple of questions. So if I start with the terminal representation, and I'm integrating with Wn of x, I will get the going terminal.
You will get? Yes, yes.
I could easily get out of this formula the going terminal of the area kernel. The going terminal of the area kernel is not specified everywhere to avoid which one equation.
Okay.
I believe this fact alone already allowed me to conclude for the going terminal correction, because we know that everywhere vector has such kind of structure. So my question is, how this different from the progress along this solution? What you call determinant representation, like you rewrite it, the good terminal to the powers of the scalar k.
So are you saying Fredholm determinant?
If you start with Wn, you sum, you integrate over all x, you sum any function, you sum over n. You will get the good determinant of the integrated kernel, of the graded integrated kernel, which is k epsilon minus n. And since built out of the area kernel, this object is tracing the distribution to the area kernel, which known to be satisfied anywhere for which number equation.
Yeah.
The array itself has exactly the structure, but you give it out for instanton, etc., etc. So my question really is how the results of the things for the instanton the structures of theory. How much is different from what we know?
Yeah. I'm sure you can probably match it exactly, but I think it's not completely straightforward because I presented this to people that know those type of things very well. And one remark that they made, for example, is that this kernel is not the typical one that they take in Fredholm determinants. I don't know why. I think it's just different communities, and probably you can transform everything into the other things with some effort. So I think in the end it could match. We never took that route because, first of all, because we know those things a bit less. And second, because that seemed a bit specific. That, for example, is not known for the theta function, and our goal was to do something universal. But it would be very interesting to see exactly how it matches, because relating it to the asymptotics of Pain-Levé, for example, could be very nice. So yeah, that's a nice point. Yeah, I can give you the the differential equation for the, so what we call Bessel, our kind of quantum curve in that case. Maybe I can erase a little bit here. So basically the two examples that we do in a lot of details are the theta function, which relates to the Bessel ODE, that when you quantize just using topological recursion, you obtain this. And it turns out that you can see that solutions of this guy, so for example, you can check it asymptotically, will be the Bessel special functions. Like instead of airy function in that airy case, you will be taking K0. K0, yes, exactly. Mhm. And the other one that we do very explicitly, and this gave us a lot more work, but it allowed us to go much more general, so we were happy to do it, is this R airy case, because in this case the quantum curve is of higher rank, higher order, sorry, or higher rank, depends on how you think about it. So this is the, this is the other case that we do, the R airy. So this is Bessel, so Bessel K0 and R airy. And here you need basis of R solutions of that guy, and that messes things up a little bit, because here you have these quadratic terms, and in principle you have R solutions, so how to combine things is not so straightforward. But in the end, there are like nice ways of combining things, so you end up also with quadratic things, even in the higher rank case. Yeah, exactly. You will have R singularities, or R minus 1, or maybe it depends on the parity of R, but okay, roughly R. And yeah, this result will work exactly the same. I just presented it in the case of one singularity because it's, otherwise things are a bit too scary, but we can prove it exactly the same when you have several singularities, and you will just have several rows with the several singularities appearing. And maybe depending on how the singularities are arranged, some of them will contribute more than the others, but you need all of them to see the right structure, at least in the R spin case, because they are just roots of unity, so you really need all of them to see the contributions properly. So you need to sum at some point contributions of them to get the right numbers. This is what I'm trying to say. Mhm. Yeah, I don't know. It's like why you choose airy. I'm just calling one the. I think you can select the other one and things will work the same. The point is that you will have two of them and one will be the minor of the other. And here you have the same. It's kind of the same symmetry. Just kind of remember that we were thinking of K0 as airy and yeah, the other one as airy. Yeah, so it doesn't change. The shape is kind of similar. I can maybe write it down, maybe here. It's kind of instructive maybe to see exactly what survives. So you will get these guys, and then you will have your Stokes guy. The Stokes guy will be equal to 2 in that case. You still have exactly the same factor. So 2 to the n over 4 pi. The same type of gamma. And here, of course, you will have the action that will change. The action, I mean the coefficient of the action, sorry, it will be 2. in this case. And you will still have the same, not the same kind of polynomials, but you will compute the polynomials appearing in the same kind of, with the same kind of procedure. And then the shape is exactly the same. So maybe I can call them beta 1, sorry. Beta kappa plus O G minus 1 minus K. And that's it. And yeah, this comes out of the fact that the instant on action in this case will be just 4x 1/2. So you see the shape is very, very similar. Yes. Yes, the interpretation is the R spin with an R spin in intersection numbers. It's basically, so it's something that needs a bit more notation. That's why I thought, okay, maybe let's skip it a little bit. So they will be guys that will depend on this as before, but they will also depend on these primary fields. The primary fields will belong to 1 until r minus 1. And this will be equal to functions over mg and bar. And here you plug with an r spin class that depends on all these primary fields times your psi classes. These guys also form a cohomological field theory. It's a more complicated one. It's in those classes, they are called R-spin Witten classes because Witten in 93 conjectured that these intersection numbers now satisfy R KdV hierarchy with another string equation. But actually the classes, I mean, he kind of gave an idea how to build the classes that more or less works for genus 0. But for higher genus, they are very hard to construct, and it gave a lot of work to algebraic geometers to construct them properly. But they became very, very important because these classes allowed to understand a set of relations in the cohomology of mg and bar that is believed to be the whole set of conjectures, just the Witten R-spin classes. So they are a very important case. Yes. We didn't think about that at all. First of all, because we didn't have like a very nice enumerative geometric problem that would be the dream to give the large genus asymptotic expansion. So from an application point of view, it looked too hard and less rewarding. But from a theoretical point of view of resurgence, understanding how to compute resurgence, I mean, instant on corrections from topological recursion and all these things, it would be very interesting to think about that. I think there will be more difficulties because already computing the the quantum curve is much harder. So the quantum curves look ugly, I mean, they look scary. But theoretically, it would be very nice. So if you have, for example, a nice enumerative geometric problem in mind, it could be a nice, like, I don't know, motivation to say, let's do it. On which spectral curve? On the mirror curve spectral curve, yes. And you are claiming that those have higher genus? Ah, okay. So that is a nice example, yes. Yeah, that looked a bit far from us. We wanted to start from... I see. Okay. So yeah, that's a very good point. That would be a very good motivation.